So welcome everybody to Science Thursdays with Brookhaven Lab. The purpose of Science Thursdays is to engage our student community and education community in STEM topics by meeting BNL STEM professionals and learn more about their work and the career path that got them to where they are today. At the end of the 45 minutes, we hope that what you hear today will spark some interest in a STEM career and perhaps even consider being part of the Brookhaven Lab community. So my name is Aleida Perez and from the Office of Educational Programs, and I'm joined by my colleague, Diana Murphy, who will manage the Q&A portions of today's discussion. Before I introduce our guests for today, a few reminders. Please submit your questions using the Q&A chat section, which is at the bottom of the Zoom app. We will try to get as many questions as we can. And if you have any issues or difficulties with the video stream, you can let IT know by making a comment in the chat section, right? So, so today I am joined by two very exciting and interesting people, by Amy Marschilok. She's a scientist and energy storage manager in the interdisciplinary department at Brookhaven Lab, and Stony Brook University graduate student Diana Lutz. Welcome, Amy and Diana. I'm glad that you're able to join us today. And Amy and Diana are joining us today to discuss batteries, energy storage applications, and career path, as it were, so we can learn a bit more to what got them to where they are today. We're going to start with Amy. Amy, welcome. How are you doing today?
Oh, I'm doing wonderful, Aleida. Thank you for the opportunity to be here. Really a pleasure.
Thank you for coming. Thank you for being part of Science Thursday. It's a pleasure. We will talk a little bit more about your career path later, but can you tell us a little bit about yourself?
Absolutely. Yeah. So I actually have been a New Yorker all my life. So I actually grew up in Troy, New York, which is upstate New York, the home of Uncle Sam. I've got just one slide here that tells a little bit about my background. So I'll share that with the group. I then got my PhD degree in chemistry in 2004, and then actually spent 3 years in industry. So I was a scientist at Great Batch Incorporated after completing my PhD. And then I spent time as a professor, first at Buffalo and now at Stony Brook. And I joined Brookhaven National Lab in 2012. So it's been really a great experience being at the lab, getting to interact with the scientists here and do really exciting work in energy storage.
Very cool. Amy, we're seeing your slides as the preview on them, whatever.
Oh, thank you for letting me know, Aleida. Let me fix that. Apologies.
No worries.
I tried to move my screens and I think I messed up my system. So let me try this again.
Not worry. I do it all the time.
How's that?
Awesome.
I'm sure all the tech savvy students are aware of what I should be doing. Yeah, great. Thank you, Diana, for the heads up too. Great. Yeah. So it's really been a fun journey for me, in different parts of New York. So it's been wonderful being on Long Island. I've really enjoyed getting to work with the talented scientists here at Brookhaven Lab, and also having the opportunity to mentor and work with students at Stony Brook University, because we're really fortunate that Brookhaven Lab and Stony Brook are just 17 miles apart. We're really close. So it makes for a really great collaborative working environment. And what I'm interested in my research is thinking about, how batteries work, how to make them work better, and different ways that we can use them to make them more effective.
Very cool. And then so for folks that may not know, the Stony Brook, it's one of the managing partners of the Brookhaven Lab, along with Battelle. So it's great. Diana, it's a pleasure having you here today. How are you?
I'm well, thank you. I'm excited to be here.
Awesome. So can you, I guess like I mentioned with Amy, we will talk a bit more about career path, but can you tell us a little bit about yourself?
So I grew up in Virginia, actually a few different places, but mostly Richmond, Virginia. Shown here, a little map. Then I went to undergrad at a small liberal arts college called Elmira College, got a BS in chemistry with a minor in bio. did a bunch of different internships, research experiences, and made my way here to Stony Brook University to do my PhD in the chemistry department. So that's the brief overview of what I've been doing.
And you and I were talking that you're in your 5th year, so you're almost done.
Yes.
Awesome, very good. So if you have any questions, you're welcome to put them in the chat, and we will try to address them as we have our conversation today. So today we're talking about batteries and energy storage, and I think the first question that I am going to ask Diana, it's for people that might not be aware of, what is a battery and how does it work, and a follow-up to that is, what kind of batteries are out there that are available for people to use?
So a battery is an enclosed system where chemical reactions are taking place that you can connect to an external circuit and get electrical energy. So it's converting chemical to electrical. You see in the middle of this slide, there's a little graphic there. What it's describing is you have a negative side and a positive side of your battery. These are made up of materials. So your phone battery, it has a graphite anode, most likely, and a lithium cobalt oxide cathode. So you have these two opposing materials. And what happens on discharge when you're using your phone, right? An electron is being pulled from the anode, and in the same at the same time, an ion in the electrolyte, an electrolyte is just something that conducts ions, moves across to the cathode. So that's the process. And so when you stick your phone in to charge it in the wall, it does the reverse. So an electron comes out of the cathode and an ion flows through the battery. So you have these simultaneous processes happening in the external circuit and the internal area. Your second question was what type of batteries, right?
Yes.
So you can see this over in the device scale portion of the slide. There's these little button cells. That would be something that's used in like a watch. There's some, this next one is a cylindrical cell. That is like a Duracell, it powers a lot of small devices in your home. Then moving forward, we have a prismatic cell in the bottom left, and then a pouch cell in the bottom right. So the top two are usually not rechargeable. There are the button cells can be lithium ion, so those can recharge, but a lot of Duracells of, right, don't recharge. So those are called primary batteries. They're typically zinc and manganese oxide, so they're made of different things, have different electrolytes, and they're made for a very specific purpose. So that's something key to batteries, is that you make the battery for the application. You can't just stick any battery anywhere to do anything. The bottom two types, the prismatic and the pouch cells, are mostly used for larger devices. So maybe like a power tool, that pack that goes onto that might be one of those, or also in electric vehicles. And when you think of larger things, like you see some of these stacks that are hooked up to the grid, it might actually be made up of some of these smaller components that are all put together, engineering kind of way.
And those two batteries that you mentioned at the end, those are chargeable batteries, right?
Yes, typically you have a lot of lithium ion ones are made with that because of the applications that they go to, but some of them you can certainly make primary or non-rechargeable batteries in those. It just has to do with changing out the materials and changing out that electrolyte in there.
Correct. Yes, that is actually, if when you mentioned the figure B, remember, the Duracells, the ones that we put on our little toys and we toss out, those are the ones that are made just for one-time use, and that's it.
Yeah,
that's it.
And what makes it so exciting is that you can actually use really different types of materials to make batteries work. And as Diana said, it really links to the application and what it needs. So sometimes you want materials that are really sustainable, that can be safe for the environment. So I see, we had a question about what makes a chemical compound good for batteries, why are zinc and manganese oxide used for Duracell. And actually, it's a great question. What's really appealing about zinc and about manganese oxide is that they're very environmentally abundant, sustainable materials. That makes them safe, that makes them really good for that use. And you heard Diana was talking about lithium ion battery. What's interesting about lithium ion, you want a system that's very lightweight, a system that's very portable and has high energy density. And that's where having that lithium chemistry is really important to make it work, because it's a very small ion. It can move very quickly, and it's got a big energy difference. And so part of what makes this battery work is the difference in energy between the positive and negative electrode. So.
And you were just talking about lithium ion batteries, and probably those are the very common batteries that I use nowadays, but also they're quite expensive to make, correct? So I guess other besides lithium, we were just talking a little bit about that. There are other kind of materials that we can use to make batteries that are more cost effective. Can you share what those might be?
Yeah. Great question. So in addition to the manganese material, another material our group's been studying for some time is iron. You know, what's great about iron, it's very earth abundant, it's very safe, and then there's the opportunity to store a lot of energy within this iron chemistry. So it's really fun working in energy storage, because we need different types of people to understand the challenges and the problem. So we work together as chemists, as engineers, as physicists. You know, people with very different backgrounds can all help with the problem, because what we want to know is, you know, what makes these ions move? How can they be stored within the solid structure? So you see, we have these different types of structures and architectures we think about, and then what makes them, you know, work safely and effectively over a long time. So it's a really fun problem, you know, working together to understand these systems.
Any kind of limitations that you find in materials? And you talk about iron and lithium, but what kind of limitations and challenges might be when you're thinking about, you know, what those materials might need to be, or the properties of those materials might need to be?
Yeah. So a big challenge is thinking about size. So when you want things to move, you know, having the right size can make a big difference. Yes. So, you know, an analogy you can think about is, you know, if you're cooking or if you're baking, right? If you try to make a cookie that's a giant cookie versus making a cookie that's a small cookie, there's a difference in how fast it heats up, right? And how fast it cooks, and then what it tastes like when it's done. So that relates to the surface area versus volume of the system. And that's an important concept for batteries, and what works both outside and inside the battery. So we think about size a lot.
Yeah, because it's the scalability of that, right? Sometimes when people see the lithium battery that is in our phone, but that's batteries that is there. Is this, I guess, and I'm speaking somebody that is not a battery person, but it's the right size to power my phone, right? It has provide all the energy that it will need it. But if you were to scale that up, let's say for the grid, it may not necessarily work, right?
Yes.
Yeah. And another consideration in terms of size is, how does the size change as the battery works? So as Dr. Marschilok was talking about, you think about the size that you make your materials, but you're trying to put ions into the material. And so how does that change the material? And we think about how it changes the size, but not only how it changes the size, but how it affects it in all sorts of other ways. So the properties of everything really matter, of the electrolyte, of the anode or the negative, and the cathode or the positive side. They all the physical properties definitely go into how they perform.
There's a question in the chat that says, has certain compounds only work for some kinds of batteries and not for others?
Absolutely, yes. So there are certain compounds that are better in terms of their weight. And there's other compounds that are better in terms of their volume. So if we want a battery that can be used, for example, for an aerospace application, you know, if you're thinking about sending a battery to the moon or having a battery on a space mission, that weight consideration is really, you know, very important. So we think about that a lot. Another application people don't think about very often is a medical application for batteries. And batteries that can be used for implantable devices could be very important. You know, we want batteries that can last a long time. If someone has a heart issue, if they need neurostimulation, neuromodulation, there's different types of devices that can help them. And you need a battery that works really effective. So there, you need a battery that can be very small and can have a very high and predictable behavior. So there's some very special materials that have been used in those batteries that are unique for that application.
And I think a good life example of this is the lead acid battery in your car. So your car battery is there to jumpstart and get you going, but it's very limited in what you can use it in. I mean, it's lead, and acid, so it does have hazards, and it's also lead is extremely heavy. So you could not try and use that battery on, you know, a space mission, as Dr. Marschilok mentioned.
And now that you mentioned the implants, right? Same that when you think about materials, not just the battery has to be able to work, do the job that is expected to do, but it has to be compatible. The materials that I use there has to be compatible with that living environment. In this case, the tissue surrounding. So there's a health component, how we might think about building this type of batteries for this kind of function too.
Oh, yes, that's really a wonderful point. And that links to something that you brought up earlier, you know, this idea of what makes the best materials. So it's something that scientists are thinking about now, you know, how available are the materials? You know, if we have batteries in more places, do we have the materials available? Correct. And then, you know, what can we do to make the batteries, you know, safe, rechargeable, sustainable? So those are all areas people are working right now.
There is Amy and Diana said the question on the chat is as going off on that last question about the compounds work in some kind of batteries and not in others. How do you determine compatibility between cathode anode materials? Is it a trial and error?
Not entirely a trial and error. So you can build a battery where you really only look at the cathode or anode. So these are typically called half cells, where you put it against a metal reference material so that you know that metal reference really well. So then you can study that one and determine its voltage, how it performs in reference to this reference. And from there, we can learn about it. And you can do the same thing with the cathode. And by comparing those voltages and how they operate, you can then pair them together into a full battery. So there's definitely methodology. It's not just pure trial and error.
Yeah, I think historically, you know, people did have to guess a lot more. You know, what's really exciting now, just as Diana said, we can look carefully at what's happening at each side of the battery. And that's where, you know, capabilities at Brookhaven Lab are so important. We can use electron microscopes to look down at the atomic level, see what's happening within the battery. We can use our giant National Synchrotron light source too, right? So we can have this very bright beam of X-rays that can go right through our battery and tell us what's happening deep inside the battery. And so that really helps people understand and do very deliberate, you know, changes to the system. So it's really advancing the science.
Very cool, because now you mentioned, you know, and because I know you're users of the light source here, and allows you also to see in command, right, as these reactions are occurring in the battery, then you can then you know, as the reaction occurred, is a better understanding how these materials, right, work together or not in terms of the function of the battery that is being tested, the materials that is being tested. So I'm assuming that you have some reference materials when you do these studies into what the expectation, you know, you may have some material that you already have a reference to it. So you might have a sense of how they should be behaving when you're testing these materials, these various materials that make up the batteries for storage purposes. Is that something that makes that kind of.
Yeah, I think
Yeah.
this goes into the synchrotron is very special. And, you know, you have to ask for time on it. You don't just get to go anytime you want. And so we really prepare for those times.
Mhm.
So we do a lot of electrochemistry, which tells us a lot about what we can expect before we go to the synchrotron. And we also look at those materials, as Dr. Marschilok said, with electron beams and other things to examine our loose materials and also the materials once we make them into those electrodes or those anodes and cathodes. And so we can kind of study every part before we put it into the hole and start to look at it at the synchrotron. And then we also have the very useful electrochemistry experiments. So we kind of know how it should run when it goes to the beamline, when it goes to the synchrotron. So I think that's a very large part of it.
Yep.
Yeah, I bet. Anything you want to say? Sorry, Amy, you want to say something?
I was going to say, and sometimes it's interesting where we get references from. So we need them to be pure materials that are well studied and well known. And often geological samples are our sources, which is really interesting because they're samples that are very thermodynamically stable. You know, they're very stable over time. They have very well-defined structures. So as Diana said, we prepare for every measurement where we have standard samples that we measure first. And often we're sourcing them from, you know, different places to get these known materials. So it's really interesting.
I didn't know that the geo samples were part of the process. That's good to know. I learned something today, as I always do. I know that when we were chatting, when we were talking about today, one of the things that we were talking about was that, you know, this is like kind of exciting time for the region in terms of wind energy, right? And the renewable sources. And so in one of the aspects that the field is thinking about is you have this energy gets generated, right? Wind and solar and all the renewable sources. One of the goals is to integrate this energy into the grid for general use. But the challenge that probably people may not be aware of is how do you take all that energy to store it, right? To integrate that into a more efficient and a better way into the system, into the grid for use. So as we start to think about, we've been thinking about it, continue to thinking about in this process, where is the battery energy storage field is moving as we're starting to, you know, move into this kind of renewable sources here in the island?
Yeah, I think what's great is that now people are starting to really cross disciplines and work together on this question. And this is a place where Brookhaven Lab has really made an investment. So there's experts in the grid and how the grid works, because what you need to know in order to integrate renewables into the grid is, when does the wind blow? You know, can we forecast that weather information? As Diana said earlier, we're going to use that wind energy to charge the battery or to store it in the battery. So we have to know how fast, you know, what time is that energy coming in? And then do we have the right battery chemistry to store it and keep it together? And so Brookhaven's made a real investment here because they've asked their energy systems experts, their grid experts, and their energy storage experts to work together. And so that's what we're doing now in this interdisciplinary science department. We're thinking about how to integrate our knowledge and then really help answer these questions with new battery chemistries and new ways of thinking about the grid. But I think it's such an important question for New York State. It's important for the nation, and New York State is a great place to be working on this because we've got so many different types of environments in New York. We've got really dense, you know, urban populations in New York City. On Long Island, we've got some more rural populations. And so upstate, we've also got different, you know, sizes of groups. So thinking about how to use that energy effectively is really part of making it work. And in our research group, we really recruit nationally and even internationally. We have group members from the Caribbean. We have group members that have come from South America. And I know that for many of us, the notion of making energy reliable and sustainable really resonates. Because if you think about events like Superstorm Sandy in New York, or like Storm Mariah, that we experienced earlier. They can be devastating to lose energy. So that's really what motivates us and makes me and Diana so excited to do the work we do.
It's a need, right? Not everybody have the access to that energy, and a reliable access to energy is a very important for all countries, whether they are very rich or very poor or not. It's the need for that. The need for it. I'm going to ask you a question because I maybe have I don't know, but you talk about the efficiency of the materials. So is the goal to make a battery that it can able to necessarily be very big, but rather the chemistry inside that battery be very efficient in either storing or I guess what I'm getting at is size is not really what we're looking for. We're not necessarily looking for a very large battery in the future. Yes. It's just a most efficient battery.
You're right. We're looking for more efficient batteries, and here's one of the things that is important about efficiency. One of the ways that inefficiency can show up is when your battery starts to get hot.
Yes.
So you might have seen this with your cell phone or with your laptop, right? Yes. Like when you have a brand new iPhone, your phone charges, it stays cool, it charges, without getting hot. As your battery gets older, it starts to get hotter, it doesn't hold a charge as longer. And if you have a small device like, your iPhone, it's okay, it's just a nuisance, but you're probably going to change your iPhone anyway. But if you have a really big battery and that battery gets hot, that can be dangerous. That can really be a problem. So when we think about batteries for the grid, that's a problem. And if we think about batteries for vehicles, that can also be a problem because as you said, cost is a big driver when people think about cars. If we want to get people into greener cars, we need batteries that are low cost, that are safe. So so efficiency is important in a lot of ways.
There's a question in the chat. I don't know whether Diana or Amy want to answer it, but is the geometry of the batteries component important for its performance? How important?
I'm not sure entirely what they mean by geometry, but I mean, if you're thinking about the materials themselves and how they're oriented,
that's what I'm guessing.
How the anode or cathode is, whether it shows up as sheets or it has some different geometry about it, that really impacts the chemistry that goes on. It really does. And thinking about on the device scale, the geometry also matters, right? So it would kind of be awkward to have like the cylindrical Duracell in your phone, right? Because your phones are all pretty flat. So that's why they created things like the prismatic cell or the pouch cell to accommodate those different geometries that you'll need. Same thing with a watch. You can't really use any of the other ones in a watch. And so having that little button coin cell type, it is definitely useful when you get to, okay, how are we going to put this into the world? But again, even at that atomic level, or a little bit above the atomic level, it really matters how it's oriented, how all the materials are oriented, and how all of the interfaces are. So, you have a material next to an electrolyte, usually next to a separator. You don't want your two things touching, next to more electrolyte and another electrode. So all of those little interfaces also, and the geometries that are there, matter a lot in terms of how it performs.
That was a great answer, Diana. And that's another great capability we have at Brookhaven Lab. We can actually make batteries that are that small button size that Diana said. We make those a lot. We can go all the way up to those pouch type batteries. So batteries that are relevant like for your laptop application. And so we can really get practice in both the manufacturing aspect and the chemistry aspect of the system. So Brookhaven's really given great resources for that.
It was a great answer. Agreed. Great answer. Before we pivot to a career path, I have one more question in the chat. It says, does charging a battery at a faster rate degrade the battery life quicker?
Great question. The short answer is yes. And the long answer is, it depends on the specific chemistry inside the battery, how much it degrades it. and exactly how fast you're trying to charge it. And that's another thing that we're working on at Brookhaven is ideas to make batteries charge fast safely. It's a really important question for vehicle technology because you can fill your gas tank quickly, and you want to be able to charge your EV at that same rate. So that's something that we're working on right now, and we're very excited about.
Cool. So we are at about what, 4:31 timeline. So let's just move. Let's just pivot here to a bit of a career path, and we have a few students that have joined us today. So I'm going to start with Diana. What did you always know that you wanted to be a scientist? How did you end up interested in STEM?
That's a great question, because I had no clue. In my senior year of high school, I took a comparative anatomy class and I really loved it. Before that, I completely just loaded up on history and English. So that got me start to think about science, and I purposefully went to a liberal arts college where I could explore what I want to do. So I didn't have to declare my major at first, and I started my freshman year taking a little anthropology, sociology, and then I took biology as well. And after that first year, I decided that I wanted to keep with biology, and I did a summer research with a biology professor at my undergrad, and that kind of cemented, okay, I really like this stuff. I like the research. I like where this is going. But there was something, I guess, a little off about biology, something I wanted. So the next year, as part of the bio program, you still had to take chemistry. And so I took the chemistry class, and I think like 2 weeks into it, I was just blown away. I loved it because it really showed me, chemistry to me it shows you how everything works. And then from there, you can figure out how to create a solution to a problem. And so I was really interested by the fact that I could use chemistry to tackle real world problems and create solutions to things. And I thought that was really cool. And so I continued on in undergrad to be a chemist. Yeah, so that's how I got to science.
That's very cool. As a bio person, I will take no offense to it.
I still got a minor in bio, and I still really like it.
And so, and there's a question in the chat that I will get to that. Whoever put it, I will make sure that I answer before that. But Amy, do you want to share a little bit about how you decided to just pursue a STEM career and about other, besides something else?
Absolutely. You know, I was I always found science interesting, and what really got me into chemistry was my freshman undergraduate chemistry course. I had a really outstanding chemistry professor, Kenneth Takeuchi. He's a distinguished teaching professor, and I'm fortunate to still collaborate with him today. So it was really my experience in freshman chemistry, and then as an undergraduate researcher, like Diana, I had the chance to do summer research as an undergraduate, to get my in the lab and see what that was like. And that was really what informed my, decision to go into science. But I have to say that I do have many different interests. I've always been interested in English as well. And I got an English minor. And I think that, if you're a student who's interested in many things, don't be nervous about, picking a path and making a decision, because I think ultimately, often your interests can come together. So, try to look at, where you think you're being successful, where you think you can have impact, and often you can bring your talents together later. So
that's a great advice from both of you. What I hear is that, the value of experiences, like research experiences, it helps you inform your decisions. Yes. And be ability to explore various topics just to see where at the end of the day where your interests lie. Some of us, some people just know from the moment that this is what they want to do, but there are a number of us that just need a little bit of need that time to figure those things out. So that's actually great advice. Diana and Amy, I'm going to ask a question that just came in about the science, and I do not want to forget. How exactly does a battery degrade is there a structural energetic change when overcharging? Those are the two questions, and I don't want to forget.
Yeah, so as I said, you have an electrode material and you're taking ions and you're putting it into that material, into its structure. So you don't even need to overcharge it. Just the act of initially putting in those ions is going to change the structure. Certain materials are going to change a lot more than others. And so that determines whether they degrade faster or slower than other materials. So that whole action of running the battery leads to the potential degradation, and it depends on the material, really how it's going to react to having that ion put into it.
And that degradation can take different forms. So sometimes it's actually a physical separation. So, inside a battery, like Diana showed, we've got these different layers and stacks, and we need them to hold together with some integrity for the battery to work. So sometimes as these ions go in and out inside the battery, these little, cracks and separations develop, and that can be a problem. Sometimes we can also have things that are dissolving, that are changing phase. So going from solid to liquid. So there's different types of, changes that can happen in the system. It's a great question.
Right. So I just really want to forget. So going back to our career path conversation, if you're a high school or college student listening today, what kind of preparation you will suggest that a student takes, in order to what kind of courses, for example, a high school student you would suggest that he or she might take, if interested in pursuing a STEM career, something similar to what you both are doing right now?
Yeah, I think if you can get background in different types of science, as a student, it can be really helpful. So I think chemistry, biology, physics, mathematics, these courses can all be very valuable for you as a high school student. And it's funny how sometimes something you learned can affect you later on. So I think the more you can be enthusiastic about each class, do your best in each class, that can help you. Because sometimes a topic can seem distant early, and later on it becomes very relevant for what you're doing.
Actually, really interesting on that. I took chemistry in high school, but I didn't get that spark in high school. So even if you don't get that spark in high school, you're not sure about any of that, I say give it a taste in college. It might be presented really differently, especially if you have the inkling of, I think it's interesting, I just didn't get it before. I think the important thing is to try things out, and to not be afraid to try things out if you don't have enough. I know a lot of people, when I was in high school, were worried about having really long lists of extracurriculars and AP classes and everything. And that doesn't matter as much going into college. It's get good grades in all of your courses, try your best on all of the exams that go into getting into college, and writing that essay, show who you are. And that's what they're looking for, driven people. So if you can show them that that's what you're gearing towards, you'll get into college, and from there it's the same thing. So just try your best to show that you're there to do your best.
I like something that you mentioned about, don't think that you don't have enough to do something. So that goes into even college and even professional careers, when we try for these internships or this type of education of, college programs, sometimes don't think that you don't have enough of what it needs to even try. Just give it a try and take that risk and the opportunity and see what that leads to.
Well, a small note on that too is in college, I took chemistry my sophomore year, just Gen Chem. And that summer I did an internship. So a lot of people would not have thought I could do a chemistry internship with only Gen Chem under my belt. So definitely don't think you don't have enough. Apply for that stuff. You will definitely be able to do it. So go for it.
There's a question that said, is chemistry just lab work? And it's more than
that's
that,
a great question. And Diana and I talk about the lab a lot because we love the lab and we love being in the lab. But actually, chemistry can be much more than that too. You know, another thing we get to do a lot is to write. You know, we get to write about what we do. We get to present the type of things we do. And I think that's another thing people don't think about in science. It can really give you an opportunity to interact with others, to collaborate, to travel. How science works, you know, can really affect how our communities work. So I think if you're excited about lab work, it can be great to be in STEM, but even if the lab work is less of interest to you, there's still a place, because there's a lot of different possibilities that exist beyond wet chemistry. So.
Well, and another side of that is, once data is collected, you can't just throw that as it is. There's a certain level of time you have to spend analyzing it. So whether that's through mathematical methods, whether you're visualizing it certain ways, whether you're doing any sort of manipulation with that, that can be a large part of the chemistry too. So it's not all sitting in lab and doing wet chemistry. And also wet chemistry makes you think of those people with like different colored liquids, you know. It's not really like that. There's a lot of different things you get to do in lab, and, you know, including what we do, again, building those batteries and then putting those batteries on instruments to test them. That's not something a lot of people would think of as chemistry, but it really is.
It is.
So it's not just all the little stock photos with solutions, although solutions matter a lot.
Yeah, that's like very good word. I mean, I'm glad that you said that, because it's more than just being at the bench, you know. And the data, and so it's the totality of all that makes the scientist, really, I think. Amy, what and Diana too, I guess, what made you decide to pursue a research career and not to, or even to go to graduate school for either of you? It's a question for both, or whoever wants to answer.
Yeah, what really motivated me to do a PhD, you know, I was really enthusiastic about science. I really enjoyed, you know, the experience of research, and through graduate work, you get to be someone who's creating new knowledge, creating new content. I mean, the whole motivation for a PhD, you know, when you create your thesis, it's a book that really speaks to something new in the field and something. So I think that opportunity to be creative, to have a chance to understand an area deeply was really what excited me about research. Yeah.
I think for me in undergrad, I got a really great span of all types of chemistry. There's biochemistry, inorganic, organic, analytical. I know I'm throwing a lot of things at some people, but there's a lot of different types of chemistry, and they're all very different. And I got a good display of that. But for me, graduate school was how to go into one area much deeper and learn much, much more. In an effort, what my ultimate goal was to work in renewable energy, work in transforming how our energy is done in the United States. And I saw chemistry as the route to do that. And I saw graduate work as the route to get to the kinds of jobs I wanted to be in terms of being a leader, in terms of being able to make decisions and have projects be led by me rather than always you know, it depends on your educational level, what sort of things you can do. So you can definitely go into the workforce as a chemist, as an undergraduate chemist, but you also get a lot of different opportunities with a PhD.
Yeah, there's a different, like you said, the different levels. And so I think at the end, I will add that at any level that a student chooses to end up, to be part of, we all have a role to play in the field. In the field of STEM, and so something to consider for those that may say, oh, maybe not graduate school, maybe not the PhD, but maybe the master, or even on the bachelor's level, or the technical level. We all have, it's a totality of all that will play a role. And so we are heading very close to our closing time. So if any advice for the audience that they don't remember anything you said, one sentence of advice that you wanted to take with them. I
think I'll end with what excites me most about science now, And I think it's really people, getting the chance to work with people. That's what excites me the most about being a scientist and the job I have now. So I just want to encourage everybody, if you're someone who wants to help people, wants to work with people, I think that's really the vision of the new scientist. And you should think about it as your career, because we need you here.
Diana?
I guess my last takeaway is try things out. Don't discount them right away. Always try new things, and don't think that you don't have enough to try them or you're not good enough to try them. And I think that's
This is awesome advice from Amy and Diana. Thank you both. Thank you for today. It was a wonderful conversation. It really was. And we are recording this, and we will post this on the Brookhaven Lab YouTube channel for people to see and re-enjoy. We appreciate all the work that you do and the insight you have given to all of us. We'd like to thank Brookhaven National Laboratory for hosting this event today, and encourage you to check out our programs. You can go to the www.bnl.gov/education to check the various educational opportunities that we have here at Brookhaven Lab for students all the way from first grade to college and beyond. Okay. You can also follow us on social media as well. Thank you so much. We see everybody for our next Science Thursday in July. Thank you, everyone. Be safe. See you next time.